Hello, let's have a discussion about hydrocarbons in that alkanes, alkenes, alkynes, and benzene. That we'll discuss in small video parts. In this part, we'll discuss about alkanes preparations. So this is alkanes 1. Here, majorly we'll concentrate on NCRT points plus few important lines. Exclusive alkanes I will give you later. This is you consider NCRT part plus few important applications of NCRT you can consider. Alkanes have a general formula of CnH2n plus 2. Alkanes are called paraffins. The meaning of paraffin is saturated, less reactive, not having any affinity over any element. That means more stable. Paraffins, and the general formula is CnH2n plus 2. We'll discuss some important methods of preparations. The first method of preparation is from aluminium carbide. This is not there in NCRT, but you will get it in carbides. So interesting, 3CH4 plus 4 aluminium hydroxide. Aluminium carbide gives you methane. Beryllium carbide, Be2C plus water gives you beryllium hydroxide plus methane for balancing purpose for water. So beryllium carbide gives you methane. Don't think that all carbides will give you methane only. It all depends. Aluminum carbide gives methane. Beryllium carbide also gives methane. But if you see calcium carbide gives you acetylene. Whereas Mg2C3, it gives you C3H4, propine. So how can we say? Very simple logic. Cl Mg2C3. What is the magnesium charge? 2. Two magnesiums are there. So charge is 4. That means you need to add 4 hydrogens. What is calcium charge? 2. So you need to add 2 hydrogens. What is beryllium charge? 2. That means you need to add 4 hydrogens. What is aluminum charge? Al4C3 compound. Aluminum charge is 3. That means 12. You need to add 12 hydrogens. But when you add 12 hydrogens, it is becoming C3H12. Is this compound possible? No. Maximum alkane is C3H8 only. That means all 3 carbons are not together. That is like 3CH4. Use some common sense here. So this is one inorganic method of preparation from carbides. Next, from alkyl halides. When these are reduced, they can be converted to RH. You need to add here any reducing agent. What are the best reducing agent? You can use zinc HCl. Actually, what happens here? ZnCl2 plus 2 hydrogens are formed, nascent hydrogens in the reaction, which can be utilized for the reduction. Or you can use zinc acetic acid. This is also fine. Or you can use zinc NaOH basic medium or acetic acid, otherwise HCl. All these are good. Otherwise, you can go for any strong reducing agents like lithium aluminum hydride is also fine. Otherwise, you can go for HA phosphorus. All you can use here. So simple examples you see: methyl chloride converted to methane, ethyl chloride converted to ethane, propyl chloride converted to propane. Very simple logic. From the same alkyl halides, one very special reaction is there which we call Wurtz reaction. Wurtz reaction is coupling reaction. Two units are going to mix. For example, Rx, one more Rx. If you are taking with the sodium metal, this part is to be out and these two R groups are joining. RR. Okay. So see some simple examples. Methyl chloride plus sodium. Methyl chloride. For easy purpose I am writing like this. When treated in the presence of dry ether, Medium is very important here. Dry ether, remember, in your chemistry paper or whenever you are saying a question, if sodium and dry ether is there, blindly you go with the um, what is the Wundt reaction. So this methyl and this methyl, you are getting here ethane. So you will get here a hydrocarbon or is an alkane with a even number of carbons. See, C2H5Cl 2 moles if you are taking sodium in presence of dry ether. I am writing De dry ether, or you can write ROR C2H5O or C2H5 taken twice O. All the meaning is same, dry ether. So what you are going to get, 2 chlorines, 2 sodiums out, C2H5, C2H5 means C4H10. Again, even number of carbons. So what do you feel? If you take methyl chloride and ethyl chloride, so chlorine out with sodium in dry ether. So this is ethyl, this is methyl. So you can expect here C3H8. True, this is right. But along with this, two methyls when they join, there is a possibility of getting ethane. Two ethyls when they join, there is a possibility of getting butane. You are not taking one molecule, you are taking some amount of methyl chloride which contains huge number of molecules. So some methyl chlorides will join with some ethyl chloride, that means methyl will join with ethyl to form propane. Two methyls will give you ethane, two ethyls will give you butane. This follows generally according to our um, studies and all. We can say this is free radical mechanism. We'll discuss about this free radical mechanism in advanced alkanes. Okay, as this is basic part, you just remember like this. So it is not good for preparing an alkane with odd number of carbons. For even number of carbons, it is a wonderful method, but for odd number of carbons, it is not good because you are going to get a mixture. So instead of this, we'll go with Corey house synthesis. What is Corey house synthesis? We'll discuss later. Some questions will be asking like this for you. If it is bromine, it is also bromine, or it is a chlorine. What happens when this is treated with sodium in dry ether like that? So when this is bromine, there is a possibility of reacting within the molecule if only one sodium is there. So like this compound is possible, you can say bicyclo compound. Otherwise, there is a possibility of getting a compound like this also, coupling. So you can say this is intramolecular and you can say this is intermolecular. These kind of questions are very interesting questions. This is just beyond ncert, but I told you now, this is one type of application. You will get questions based on this type of concepts. So this is about Wundt reaction. So two methods we were discussing from alkyl halides. One is reduction, second is Wundt reaction. We'll go with one more, that is decarboxylation. Decarboxylation means D means removal minus carboxyl group means COO group. COO group removal purpose we are going to use soda lime. What is soda lime? Soda lime is NaOH caustic soda, CaO quick lime. This combination is called soda lime, which is much better used for removal of CO. As we are removing one COO group, that means one carbon is definitely going to decrease here. When carbon decreases, that reactions are called carbon degradation reactions. Carbon degradation means number of carbons are going to decrease. Carbon degradation reactions. So decarboxylation means removal of COO by using soda lime. It's a combination of sodium hydroxide and calcium oxide. Here number of carbons are going to decrease. That's why this is called carbon degradation reaction. Have a look at this. CH3COONA when treated with sodium hydroxide and calcium oxide and heated, this part is out. So this CH3, this H is going to give you methane. So methane comfortably you can prepare here. See one more. CH3, CH2, COONA, NaOH and CaO. Heating. So very simple part. This will go out. One hydrogen you need to add here. This part will become as C2H6. Ethane is going to form. Your parent compound contains 3 carbons, 1, 2, 3, but here only 2 carbons are there. Number of carbons are decreasing, that's why this is carbon degradation reaction. So you can prepare methane ethanol. I forgot to explain you one point in Fuji reaction. You cannot prepare methane because that's a coupling reaction. Minimum 2 carbons are required. Methane cannot be prepared by Fuji reaction. Okay, come back to this one. So we were discussing decarboxylation. We'll go with one very interesting reaction, that is Kolb's electrolysis. What is Kolb's electrolysis? We are going to take again salt of acid, carboxylic acid, aqueous solution, that means water, and we are going for electrolysis process. On electrolysis, you are going to get products at cathode and anode. We'll see one simple example. CH3COOK plus water. On electrolysis, you are going to get ethane plus carbon dioxide plus potassium hydroxide plus hydrogen gas. These two are formed at cathode. No, these two are formed at anode. Right? No confusion, I will give you the mechanism. Just have a look. CH3COOK gives you CH3COO minus and K plus, right? CH3COO minus means this is having 2 electrons, 1 electron gained from potassium, actually 1 electron is its own, and this is an anion. Anions will go to anode. This will go to anode and lose 1 electron. Of these 2 electrons, 1 electron it is going to lose, minus electron. When it loses electron, it becomes like CH3 C double bond O with 1 electron dot. 1 electron it has lost. So this is happening at anode. I was writing cathode there. Sorry for that actually. So it is at anode. Now what happened? CH3 C double bond O 1 electron is here. This electron will come like this. 1 electron from here will come here. 1 electron will go. So this part will become carbon dioxide, C double bond O, and this will also become double bond because of these 2 electrons, and this part will become methyl free radical. When methyl free radicals are formed, the 2 methyl free radicals will join to form ethane. So this ethane and the carbon dioxide both were formed at anode. The potassium ions or the sodium ions will react with water to form KOH and releases H plus ions, you can say. These H plus ions will go to these cations, so go to cathode and they gain electrons and release in the form of H2. 2H plus 2 electrons gives rise to H2. This is the reaction at cathode. Fine. So I'm writing again the reaction CH3COOK plus H2O for balancing purpose. C2H6 plus 2CO2 plus 2KOH plus H2. H2 is at cathode. These two are at anode, and this will be in the solution. The solution nature will be alkaline because of the presence of KOH. Alkaline nature. This is your question. You can see these kind of questions in your objective bits. So now, the one important thing, you cannot prepare methane because minimum 2 carbons will be there. So methane cannot be prepared by Kolb's electrolysis. Kolb's method you cannot use for methane. Remember this. These kind of questions are very common. Now, if I want to prepare ethene, then what should I do? CH2, if I take this compound, then what happens? Very simple logic I am showing, you see. If this is the compound, okay, these two will go to cathode, hydrogen out, KOH. This is water I was writing, H2O, H2O. Hydrogen out, KOH, KOH. This is CO2, CO2. And this part is CH2, double bond CH2. One bond will extra come here, CH2, CH2. Simple logic. If you want to get ethane, then what do you have to do? CH, double bond CH compound you take, COOK, COOK. If this is hydrolyzed, for easy purpose I am writing water as a OHH. So see the products. This is one product with one bond extra. CO2, CO2. All these are H anode. KOH, KOH. Solution H2 at cathode. Anode products, cathode products. So this kind of questions they will ask you. If you want to prepare 2-butene, CH3C, CH3. This kind of compound you take, COOK, COOK plus water, CO2, CO2 out. What happens? This bond you can say here. Of course, this will be again free radical mechanism. No? So you will get here 2-butene. So just see the product. Otherwise, just see the question what is asked in the product. Based on that, you take the structure of the reactant molecule. This is one important question. This is all extra. Okay. One basic reaction is given in your NCRT. Just these for your satisfaction purpose, for your little extra information purpose, I am giving you this. So next one is from alkenes, CH2 double bond CH2. If you are adding hydrogen in presence of nickel at 200 degrees Celsius, the reaction is called Sabatier-Senderens reaction. Sabatier-Senderens reaction. CH2 double bond CH2 plus H2. Okay. Sabatier-Senderens reaction. You can use here palladium and platinum also at room temperature conditions, enough for this. So alkenes means whenever double bond is there, this will be converted to single bond. If you have CH triple bond CH, if you add hydrogen in presence of nickel or palladium or platinum, anything is fine. This will be converted first into CH2 double bond CH2. This will be converted to CH3 single bond CH3. Same reagents you use here. Again by adding hydrogen. So first alkynes to alkenes, then alkanes. But interestingly, one question you see, CH3, C, triple bond, C, CH3, that is 2-butane. When 2-butane is with you, if you are using sodium in liquid ammonia, otherwise you can use hydrogen, palladium, barium sulfate in presence of quinoline. This reagent is called Lindlar's catalyst. In this case, the product will be like this. In this case, the product will be like this. Both cases are partial reductions only. We are doing just a partial reduction. Here, this compound is trans, whereas this compound is going to be cis. Only alkyne is converted to alkene. The reaction is stopped at alkene place. But in order to get the transform, we need to use sodium in liquid ammonia. And to get cis one, you need to use Lindlar's catalyst. That is hydrogen, palladium, barium sulfate in quinoline. So remember, this is one very, very, very important point. In partial reduction from alkynes, if you want trans alkene, use sodium in liquid ammonia. If you want cis alkene, use Lindlar's catalyst, hydrogen, palladium, barium sulfate in quinoline. One very, very, very important reaction this is. Then few important physical properties. C1 to C4 are gases, that means up to butane. C5 to C17 are liquids. C18 and above all are solids at 298 Kelvin. That means under normal conditions they will be solids. Solubility, they less soluble or is insoluble in water because the concept is known to you. Like dissolves in like. So insoluble in water, water insoluble. Your questions will be based on boiling points. Boiling points directly proportional to molecular mass. So if you are looking at methane, ethane, propane and all, the boiling points will be continuously increasing. Methane will be lowest because molecular mass is low. And boiling points, again, one another important point is depends on length of the carbon chain. If length is more, the boiling point will be more. Look at this. Here five carbons are here, five carbons, but one four carbons in a chain and one is methyl. Here three carbons, two carbons as methyl groups. Now length is more in this case, so this is having more boiling points. You can expect a question based on this. So boiling points depends on length, because when length is more, the surface area will be more vulnerable attractive forces will be there. That's why the boiling point will be more. One important line. Melting point case, when you see, some books mention that when you are comparing the melting points of adjacent groups, the even numbers will be having little more. But actually methane, then propane, then ethane, then butane, then pentane, this will be there. This is the order. So only here that exception is there. Some melting point of ethane is approximately 100, I think. So it will be around 88 like that. So methane to ethane actually increases, ethane to propane decreasing melting point. But this is the only exception I felt. Remaining, no need to remember this kind of things. So this is enough for preparations. We'll discuss about properties in next class. Okay.